Today we're going to look at some nice techniques for graph sketching. Now, in fact, you already know something about graph sketching. You can use scaling or translations, or do you remember the method of completing the squares? But what about an example like this? F of x equals 3x to the fourth plus 2x cubed. How would you go about that? Well, I suppose the first thing to do is to factorize that expression. And if you do that, then you can see immediately that when x is equal to 0, f of x is 0, so the graph goes through there. And when x is equal to minus 2/3, again f of x is 0, so the curve goes through a point roughly there. And having got those two nice easy points, you might say, well, let's plot a few more. When x is minus 1, it turns out that f of x is 1, so the graph goes through there. But suppose we'd only got those 3 points. I suppose what you'd do then is you'd draw a graph like that. I think that's what I'd do. That seems a reasonable thing to do, a reasonable suggestion for the graph. But what do you think of a method like that? It's a bit rough, isn't it? And I'm not at all sure that I haven't missed out something really important, some important feature about that graph. And in fact, there might be lots of graphs which go through those 3 points. And if we plotted them all accurately, we might find that they look very different. Have a look at these. Well, you've just seen there are thousands of curves that go through those 3 points. And which one should we choose? For example, look at these. Here are just 4 of them. Which is the right one? Well, as it happens, it's the one in the top right-hand corner. It's that one. That's the right graph. But how would I know? Well, you might say, why didn't I plot more points? Sure, I could plot more points, loads and loads of them. But there's one fundamental difficulty with that process, and let me show you what it is. Look at this. Here's a function, 10,000x over 10,000x minus 1. And I've chosen that function very carefully because when you put in integer values, minus 2, minus 1, and so on, you get out the value 1. If you work it out on a calculator, you get 1 in almost every case, except at the origin, you get the 0. And if you plot those values like this, not forgetting to put this one down at the origin, there, and then said, well, on the basis of that information, what graph should you draw? Well, I mean, I know what I would do. I'd put it in through like that, wouldn't you? Down, along like that, up and along. Very reasonable thing to do. But in fact, the graph looks like that. So you've got some strange behavior between 2 of the points that you've plotted. Well, what we need, you see, is some method which will determine when that sort of behavior happens. And some method which will show us that the function is nice and smooth between points like that. What sort of method? Well, it's bound to be a calculus method, isn't it? This is a calculus block. And it's going to involve the derivative of the function.
Now, Graham has hinted that the calculus can be used as a shortcut to plotting a lot of points. Well, I'm going to show you how we can do that by using facts like where the derivative is 0, where the derivative is positive, and where it's negative. So let's look at a typical function and its derived function. In this region, the function is decreasing. Its tangent line has a negative slope. So the derivative is negative, and the graph of the derived function is below the x-axis. Here the tangent line is horizontal. It has 0 slope, and so the graph of the derived function intersects the x-axis. Now the function is increasing. The tangent line has a positive slope, and the graph of the derived function is above the x-axis. The tangent is horizontal again. The graph of the derived function intersects the x-axis. Now the slope of the tangent line is negative. And here, the slope of the tangent is 0. And finally, it's positive again. Now we'll look at that again, but this time we'll focus on whether the lower curve, that is the curve of the derived function, is positive, 0, or negative, and predict for yourself what the upper curve, the curve of the original function, is doing. The derivative is negative. Now what is the function doing? Well, the slope of the tangent line is negative, and so the function is decreasing. When the graph of the derived function intersects the x-axis, the derivative is 0. Therefore, the tangent line is horizontal. Now the derivative is positive. What is the function doing? It's increasing. Now, what did we learn from that? We saw that facts about the derivative tells us something about the behavior of the function. Here we have the two curves that we saw in the computer animation. Now, notice on the dark shaded area, the derivative is negative and the function is decreasing. On the light shaded area, the derivative is positive and the function is increasing. Now, at this point, where the derivative is 0, that means then that the slope of the tangent line to the graph is 0, and therefore the tangent line is horizontal. At these 2 points, also the derivative is 0, and so at these 2 points, we have a horizontal tangent. Now, at these 3 points where we have a horizontal tangent, we have what we call a local extremum. Now, the derivative is going to tell us what kind of extremum we have. For instance, at this point, where the derivative is 0, and the derivative changes from negative to positive, at the corresponding point here, the function changes from decreasing to increasing, and therefore we have a local minimum. Now here, where the derivative is 0, and the derivative changes from positive to negative, here, the tangent line slope of the tangent line changes from positive to negative, and so we have a local maximum. Here we have a local minimum for the same reason that we had a local minimum over here. Now, what I've given you is the first derivative test.
Well, that's the first derivative test, and that's what it means. But let me show you how you use it. I've got an example here, a very simple example of a function which you could probably sketch already. The first step in the first derivative test is to differentiate, and you get f dashed at x is equal to 2x minus 1. Now you look for values of x which make the derivative 0, and it's very clear in this case that x equals 1 will make that 0, so let's store that up there, x equals 1, and for that value, f dashed of x is 0. Now you look a little bit below 1 for values of x less than 1. If x is less than 1, this is going to be negative, and if x is greater than 1, f dashed of x is going to be positive. So now what does that mean for the slope of f? Well, negative slope, it's going down. 0 slope, it's going along. Positive slope, it's going up. And so the first derivative test tells us that there's a local minimum there. Now what about sketching the graph? Well, all we need to know in addition to that is that when x is equal to 1, f of x takes the value 2. So the graph goes through the point x equals 1, y equals 2. It goes through there. And we now know there's a local minimum there. So the graph is something like that. So that's how you use this process for finding local minima, but you can equally well find local maxima by the same process.
Now that example was rather easy to do by the first derivative test. However, there are examples which are not as simple. There is another test, however, which gives us a shortcut for finding the local extrema. And I think you're going to like this test. To determine the test, let's consider our original function again. Remember, where we have a local minimum, the derivative changes from negative to positive through 0. So the derivative is increasing. Where there's a local maximum, the derivative changes from positive to negative through 0. So it's decreasing. So we're now interested in the increasing and decreasing behavior of the derivative itself. So let's store the original function and look at the behavior of the derivative's derivative. That is the second derivative of the original function. Where the first derivative is increasing, the second derivative will be positive. When we have a horizontal tangent line to the graph of the first derivative, the second derivative will be 0. When f dash is decreasing, f double dash will be negative. And when f dash is increasing, f double dash will be positive again. So now we can use this second derivative to predict the behavior of the first derivative. Remember, it was these zeros of the first derivative that corresponded to the maxima and minima of the original function f. Starting from the left, where f double dash is positive, f dash is increasing through 0. Now in the middle, f double dash is negative, and f dash is decreasing through 0. And on the right, f double dash is positive, and that means that f dash again increases through 0. Now let's see what the sign of the second derivative at these 3 points tells us about the original function f. Here we have the 3 curves that you saw in the computer animation. The curve representing the original function, the curve representing the first derivative, and the curve representing the second derivative. Now, notice in this dark shaded area that the second derivative is negative. And so that means that f dash is decreasing. Now, it's decreasing through 0 from positive to negative, and so therefore at this point on the graph of f, we have a local maximum. Now, in the light shaded area, the second derivative is positive. So the first derivative, therefore, is increasing. It's increasing through 0 from negative to positive, and so therefore at this point we have a local minimum. And similarly, we have a local minimum here for the same reason. Now what I've given you here is what we call the second derivative test.
You know, what Lewis said is right. Everybody loves the second derivative test, and let me show you why. Look at this function. In fact, it's the function we started with at the beginning of the program. 3x to the fourth plus 2x cubed. Do you remember I tried to sketch that? Well, with the second derivative test, what you do is this. You differentiate that, and it's going to come out to be 12x cubed plus 6x squared. Now, we want to find out where that first derivative is 0, so it's quite a good idea to factorize it. And it comes out to be 6x squared into 2x plus 1. So we can now see that this derivative is going to be 0 when x is equal to minus a half. Let's store that up there. And when x is equal to 0. And I'll put this way over there for reasons which will become apparent later. And we know that At those two values, the derivative is 0. Now the next stage is to differentiate again. See this line here? You differentiate that and you get 36x squared plus 12x. Now all you've got to do for the second derivative test is to put in there the value x is minus a half. And as it happens, it turns out to be positive. And now all you've got to do is to say positive second derivative, first derivative 0, therefore there is a local minimum at that point. Just like that. There's no problem with it at all. Let's now have a look at the other point where f dash of x is equal to 0. Here, it happens at the point x equals 0. But there, when you put x equal to 0, we get f double dashed equal to 0. So the second derivative in that case tells us absolutely nothing. Now let's recap the situation so far. We've got two methods which tell us something interesting about the graph, where it has a local maximum or a local minimum. But now we're going to have to do something a little bit more sophisticated. We're going to have to look at the second derivative to get much more detailed information about the graph. And bear with me for a moment while we look at the second derivative again. This time, here's the second derivative. I want to factorize it again, as I did before with the first derivative, because I'm going to look for values of x which make the second derivative 0. And you can see, can't you, that when x is equal to minus a third, this is 0. And of course, when x is 0, we already know f double dash of x is 0. And in fact, I can do more than that. I can show that the second derivative is positive until you get up to the point minus a third. Let's put it in there. Negative between minus a third and 0, and then positive from there on. But that's all very well. I mean, I found that information fairly easily, but what does it mean? You see, what we need is some way of interpreting what the behavior of the f double dashed does to the behavior of f.
Okay, so the question is, what do properties of the second derivative tell us about the behavior of a function? For instance, here the second derivative is 0 and it's changing from negative to positive. What happens at this point on the graph of the original function? Similarly, here the second derivative is 0. What happens at this point on the graph of the original function? Watch and see. We're interested in the points where our second derivative is 0 and changes sign. To what do these zeros correspond on the graph of the first derived function? They correspond to the local maxima and the local minima of the first derived function. But to what do they correspond on the graph of our original function? These points don't look very significant, but watch the behavior of a moving tangent very carefully. Let's make it clearer with a little arrow. At precisely the points that interest us, the tangent changes from being below the curve to being above the curve, or vice versa. Here the tangent line is below the curve. In this section, the tangent line is above the curve. In this section, the tangent line is below the curve again. We say at these two sections, the graph is concave upward. At this section in the middle, the graph is concave downward. A point at which the concavity changes is called a point of inflection. So, the zeros of f double bar correspond to the points of inflection of the graph of our original function f. All right, we've learned some new terminology. We've learned about points of inflection, and we've learned about concavity. At this point, we have where the second derivative is 0 and changing sign. we have a point of inflection on the graph of our function. Here, the second derivative is also 0. It changes sign. We have a point of inflection on the graph of our function. Now, the second derivative also tells us about concavity. Here, where the second derivative is positive, the graph of our function is concave upward. Here, where the second derivative is negative, the graph of our function is concave downward. Now, how are you going to remember those two facts? Well, there's a simple way. Think of the portion of the graph as being a bowl holding water. Now, when the second derivative is positive, the water stays in the bowl, and so the graph is concave upward. When the second derivative is negative, here's our bowl, the water falls out of the bowl. So the graph is concave downward. All right? Here, where the second derivative is 0, because the second derivative is changing from negative to positive, we have a point of inflection where the graph of the function changes from concave downward to concave upward. And that's it.
Well, with all that information, I should be able to interpret what I said about the f double dash a moment ago. Here we are on this bottom line here, you see? Look at this. Positive second derivative, 0, negative. There's a point of inflection there at minus a third. And also at the origin at 0, because it goes negative, 0, positive. So there's another point of inflection. Also, I can see that from here, positive second derivative, it's concave upwards. It holds water, as it were. In here, it's negative. It's concave downwards. Here, positive, concave upwards. I've got more information too. At this point, at minus a third, it turns out that the derivative is positive. The thing is going upwards, like that. And by accident, actually, at this point, the derivative is 0 at the same point as the second derivative is 0. Now, with all that information, I can have a jolly good go at sketching the graph. Here we are. Remember what I said before? The graph goes through the origin, and it goes through the point minus 2/3, which is about there. But also now, you see, I know that there is a local minimum minus a half, that's minus 0.5. I know that the graph is concave upward until I reach minus a third, which is about there. The slope there is positive. It's then concave downwards until I reach the origin. The slope there is 0, and then concave upwards from there on in. So that then is my attempt to sketch the graph of this function f. But I know what it looks like. Remember this? Here is the attempt that we got from the computer. Well, I think you have to admit that that's not a bad attempt to sketch that curve. And in fact, you know, we've done better than the computer could do, because the computer plots curves like that by putting in lots and lots and lots of points. And the computer isn't sure that things don't happen in between those points, but we are sure. Our methods are much more powerful. In fact, it's better than having your own private computer at home.